In complex industrial operations, a massive turbine can lock into place, pass every safety inspection, and hit every performance target. Conventional risk registers score these physical assets in total isolation. They give the hardware a clean bill of health, while completely missing the larger system dynamics at play, resulting in a fatal catastrophe. If the pipes hold and the valves work exactly as engineered, where exactly does a systemic disaster begin? In reality, disasters develop in the invisible spaces between those perfectly adequate systems, long before a pipe ever breaks. These boundaries are the exact moments where information, responsibility, and decision authority are handed off from one team or digital interface to another. This is the six-layer framework. It elevates non-physical layers, like human decision-making and institutional governance, to the exact same status as physical hardware. To predict the next disaster, an enterprise must stop staring at isolated assets and analyze the invisible digital and human seams connecting them. This illustration defines the most dangerous node in this systemic architecture, the pivot domino. When it fails, it removes critical downstream information completely silently. There is zero physical warning that the data operators rely on has become unreliable. At the Toledo Refinery, the fuel drum's physical instrumentation actually reported levels exactly as designed. The metal and sensors did their job. This flow diagram maps the real breakdown, which happened in the digital and institutional layers. An escalating flood of digital alarms masked the true severity of an overfilling fuel drum, and the facility's institutional escalation protocol entirely collapsed under the data volume. At Toledo, the physical components held. The disaster itself was a paralysis of human operators, blinded by excessive data and stranded without a clear path to halt operations. This chart details the net fragility matrix, a scoring instrument designed to mathematically rank the severity of these boundary conditions before they fail. Looking at these three gauges tracking Toledo's silent failure profile, the first metric hits maximum severity, high dependency concentration. Operators were forced to rely on a single, unverified digital alarm system as their absolute sole source of truth. The other two gauges reveal equally dangerous flaws. Replaceability scored extremely low, meaning there were zero alternative ways to verify the threat. Command continuity also failed, representing a total loss of authority across a 24-hour shift change. By calculating these specific metrics, investigators can map the exact path a disaster will take through an organization's hierarchy, long before a single spark ignites. Is this invisible architecture of failure unique to refineries, or a systemic law across the board? In 1988, the Piper Alpha platform exploded in the North Sea, setting a grim historical baseline for offshore catastrophic failure. Fast forward to 2010, the Macondo Deepwater Horizon blowout presents an entirely different era and environment. This matrix compares Piper Alpha, Macondo, Statford B, and the Toledo Refinery. Despite spanning 35 years and different environments, all four share the exact same systemic pivot domino failure profile. These boundary information failures form a recurring structural pattern hardwired into complex operations. This Venn diagram highlights a crucial convergence. Independent academic safety science has reached the exact same conclusion. Safety is a highly dynamic control and feedback problem based on continuous data flow. Because this pattern repeats across decades, the priority shifts from simply maintaining hardware to aggressively defending the decision pathways between those systems. When operations are this interconnected, protecting the physical asset is only half the job. If the pathways connecting them are left unmonitored, the silent cascade has already begun.